Good afternoon. This is Andy Schweitzer, and we're continuing on a series of videos here talking about chemical reactions. For a chemical reaction, and the power standard is essentially that chemicals in chemistry undergo chemical reactions or rearrangements. And in this chapter, the chemical reaction that we are going to be highlighting is that of combustion. So again, there's no difference in the atoms before or after. They just simply rearrange into different patterns or different groupings. So we're not gaining atoms, we're not losing atoms. That's very important for conservation of mass. But essentially, we have our reactants and we have our products. This is very often referred to as the yield sign. Yields. Keep in mind that if we have a substance, we designate this substance as being the reactants. As the reaction takes place, it can go fast, it can go slow, but we'll have some sort of rearrangement as to how this happens. It just depends on the chemical reaction. One example of a chemical reaction being combustion is it's quite simple. We're looking at essentially hydrocarbon, carbon, hydrogen, I'll include oxygen in as well. Some hydrocarbon, we're going to add oxygen to this particular item, and we're going to get a certain kind of product. And that product always is CO2, carbon dioxide, and water. Now, we would call this complete combustion in the sense that we're fully oxidizing all the carbon and hydrogen. If you were to restrict the oxygen, you would get a slightly different product. Again, we're burning some sort of hydrocarbon, doesn't make a difference, but we would get carbon monoxide and water. Just we're almost always doing complete combustion, so unless they tell otherwise, we call this complete versus incomplete. Lots of examples where incomplete combustion takes place, but in your furnace, if your furnace is functioning properly, then maybe some of this could get leaked into your house, and that is bad news for people in the house. So it's quite poisonous. All right, so let's look at a little bit further this combustion reaction. Again, if we take, let's say, methane, CH4 plus O2 yielding carbon dioxide and water. These are my reactants, these are my products, so keep in mind you would have the same number of methane carbons, hydrogen, and oxygens on each side. So writing the reaction out is quite simple, and we're going to also look at an idea of balancing. I'm going to walk through a sort of longhand method of balancing. Some people like this method, some people just balance in their head by inspection, whatever. But this is a unique method if sometimes balancing is difficult for you. Under the yield sign, I would put down what I call my inventory. What do I have of these guys? Again, the atoms are simply just rearranging. I don't have a creation of elements or deletion of elements. So I have one carbon on the left side, one carbon on the right side. I have 4 carbons on the reactant side, and I have hydrogens, and I have 2 hydrogens on the product side, and then I have 2 oxygens on the product 3. So I have 1, 2, and a third one here is 3. And I have, in this case, oxygens. I have 2 over here, which is this 2 right here. So the subscript right here only deals with the item right to its left. We have an opportunity to add coefficients out front, and right now they all are essentially 1 and we can, at this point, change the coefficients to match up the atoms from the reactant side to the product side. We cannot, however, change the subscripts. Changing the subscripts changes the actual atom itself. Now, one thing that I often point out to people is that there in nature are some elements that sort of arrive in pairs if they are element. So, for example, this is the number 1 here, just to make sure you understand that. But we call this the super 7, and they are we call diatomic atoms, elemental diatomic atoms. And it would be oxygen, nitrogen, fluorine, chlorine, bromine, and iodine, and of course the last one is hydrogen. We call it the super 7 because there are 7 of them. On the periodic table, they happen to form the shape of a 7. Nitrogen starts at number 7, and there are 7 of them all together. So either way, that is why there is 2 starting out right off the bat here. So we look for them all by themselves. Now this guy here has a 1 right here because that is the formulation of the molecule water. This molecule is hydrogen peroxide. It can be a very dangerous chemical. Bleaches your hair at high concentrations, quite deadly. So big difference between these 2 chemicals. This is the water, this is hydrogen peroxide. So in order to not change the identity of the substance, we want to change the quantity of them, not necessarily the identity of them. Which is why when we balance, we're simply going to change the coefficients as opposed to the subscripts. Changing coefficients does not change the identity of the element or the substance. Alright, so at this point, combustions are the hardest ones to balance. So in this case, just a heads up that I always balance in the direction of carbon, then hydrogens, in this order. And you will see it balances quite simply every time. So start with carbon first. I have 1 and I have 1. And my inventory shows 1 on 1. Hydrogen, I have 4 and I have 2. So I'm going to just simply bump this guy to a 2. 2 times 2 is 4. And that bumps this guy to a 4. But again, it also bumps the oxygen. 2 times 1 is 2. Plus the original 2 that was here bumps this guy to 4. And finally, because the oxygen is all by itself here, I chase this guy back, update the oxygen. And in that case, I require a 2, because a 2 times a 2 is a 4. And this is now balanced. If the oxygen doesn't balance, the only reason why it wouldn't balance is if you have sort of an odd and even issue, where if I need 5, but I can't get a 5 by multiplying, I can never get 5 on this left-hand side here. In that case, if your oxygens won't balance because of an odd even problem, simply take and double this guy to a 2 and rebalance, and it will balance every time. It will balance, it would honestly balance every time if you started this thing out right here with a 2. That would always balance every time. But we would end up with potentially with something like this: 2 CH4s plus 6 O2s, 2 CO2s, and 2 H2Os. Now, so this would be a 4. Now, technically, this thing is balanced, just like the top one's balanced. We have the same number of atoms in H1, and the ratios between each are all the same as well. But technically, at this point, we just want, anytime you see coefficients that can be reduced, we reduce this guy down to a 1, down to a 3, down to a, somehow oh, I'm sorry, I misread that. That is a 2 right there. 2 times 2 is 4. Alright, so either way, that had to have been a 4 here, which gets dropped down to a 2, and which just gets dropped down to a 1, and this gets dropped back down to a 2. So either way, whenever you look at your coefficients, if possible that they can be reduced, then we reduce them. Only the coefficients. Okay? Another example of a balancing. Let's just give one more example here. Let's try an alcohol, for example. Let's go ethanol. C2H5OH. That's ethanol. So every combustion reaction will run in with oxygen and produce carbon dioxide and water. Okay. Um, Balancing wise, okay. Again, you can do your inventory in this fashion, or you can just do it by inspection in this fashion. So I have 2 carbons, so I need to put a 2 here. I have 5 plus 1 is 6 hydrogens. So I'm going to make this guy product 6 by 3. 2 times 3 is 6. And then oxygen-wise, again, chase the oxygens back. I have 3 oxygens here. And then 2 times 2 is 4, plus 3 is 7. And there's just, well, I shouldn't say that. I have, to get this guy to 7, I have 1 located right there. So I have 3 here. 2 times 3 is 6, plus 1 more is 7. And that thing is actually balanced. If not, I would increase this guy to a 2, and I would be good to go. If you want to take a moment, I'll give you one more practice. Feel free to pause the video and give this one a try on your own. Let's do isopropyl alcohol. This is this chemical. All right. So take a moment, pause the video if you want to try it, and then I will pick it up at that point. All right. So again, let's try and burn this thing. The formula for this guy is C3H 1, 2, 3, 4, 5, 6, 7, and then OH plus O2 yields carbon dioxide and water. I have 3 carbon. Hydrogens, I have 7 plus 1 more is 8, which is 4. Oxygen-wise, I have 4 here, plus another 6 there is 10. Now in this case, I need to get 10 over on this side. I have my 1 right here, so I can't get an even number here. So no matter what I do with this coefficient, I get an odd number. So I'm going to dump this guy up to a 2, which bumps this guy to a 6, which bumps this guy to an 8. And now, rather than I have 8 plus another 12, I have 20. And before I had 10, now I have 20. I doubled it. So this guy now needs to become 20. I have 2 right here, 2 oxygens, so I need 18 more from that guy, because I have 2 located here. So this is going to be a 9. So my balanced and simplest form is located right here. 2, 9, 6, 8. Keep in mind, for the more complicated ones like this generally is odd. It's quite common that number is odd. And we'll stop there. Hope that helps out.